Are we really getting the most out of our AI models? Well, it turns out we might be leaving a massive amount of their reasoning power just sitting on the table. Today, we're going to dive into some incredible research that found a surprisingly simple trick, a hidden knob, if you will, that unlocks a whole new level of genius in the AI we're already using. So here's the game plan. We'll start with this weird problem where AI performance just hits a wall. Then we'll uncover the hidden dimension that holds the key. After that, we'll see exactly how it unlocks the model's true potential, find out how to do it efficiently, and finally, think about what this all means for the future of AI.
All right, let's kick things off with a puzzle that's been bugging researchers. The point where just throwing more power at an AI doesn't actually make it any smarter. I mean, this is the big question, right? When you give an AI a really tough problem, like a complex math puzzle, what's the best way to get it to spit out the right answer? For a long time, there have been two main camps on this.
On one hand, you've got something like reinforcement learning. Think of this as putting the AI through an intense, expensive training boot camp. You're fundamentally retraining it to be smarter. But on the other hand, there's a much simpler idea. Why not just ask the AI for hundreds, maybe thousands of different answers, and then just pick the best one? It's less about training and more about just giving it more shots on goal.
Now, this is what happens when you follow that more is better logic. And you can see it right here. As you go from about 100 samples to over 1,000, performance jumps up. Great, exactly what you'd expect. But then, something really weird happens. When you push it way further to over 13,000 samples, nothing. The performance just flatlines. It hits a brick wall. All that extra compute, time, and money gives you zero improvement. The AI is officially stuck. So why? Why does this happen? Well, the clue to cracking this whole mystery lies in a setting that a lot of people just ignore. It's a little parameter called sampling temperature. Temperature is basically a creativity knob for the AI. If you turn it down low, the model gets really focused, very conservative. It sticks to the most obvious, probable answers. But when you crank that temperature up, you're injecting randomness. You're encouraging the model to get creative, to explore some wilder, less obvious ideas. And this right here is the big aha moment from the research. What if the issue isn't the number of tries, but the style of those tries? The researchers found out that the kinds of problems an AI can solve changes a lot, depending on where you set that creativity knob. This table shows it perfectly. Look, question 1 is easy. The AI gets it no matter the temperature. But then look at question 2. It's impossible at low and high temps, but it unlocks right at that medium setting. And question 4 is the total opposite. It's only solvable when you let the AI get really creative. So you see, trying to solve every problem with just one temperature setting is like trying to open 4 different locks with the exact same key. It's just never going to work. So now that we know different temperatures are keys to different problems, the solution becomes kind of obvious, right? This is how you build a powerful new technique.
Instead of spending all your compute power generating, say, 1,200 samples at just one temperature, you generate 100 samples at 12 different temperatures. You see, you're not just scaling up your effort anymore. You're scaling it out across a brand new dimension, exploring what the model can do in a much, much smarter way.
Okay, so the big question is, does it actually work? Oh yeah, absolutely. On average, across 5 different tough reasoning benchmarks, this simple change in strategy boosted performance by a massive 7.3 percentage points. And remember, that's with 0 extra training for the model. That is a huge gain for such a small change.
The reason it's so crazy effective is because problems really do fall into these 4 buckets. The old way of sampling is fine for the easy and medium ones, but it completely misses those hard problems. Those are the ones that are like a special lock that only opens with one very specific key. By trying lots of different temperatures, you give yourself a much better shot at finding that perfect key for every single hard problem.
And here's where it gets really nuts. This technique lets a standard off-the-shelf model achieve performance that's on par with a super expensive, specially fine-tuned model that went through all that costly training. You're basically getting the performance of a major upgrade without paying for the upgrade. It's amazing. Now, you're probably thinking, okay, that's cool, but sampling at a dozen different temperatures sounds incredibly expensive and slow. And you'd be right, but the researchers came up with a really clever solution to make this technique totally practical.
They call it the multi-temperature voting system. And here's the gist. First, it generates just one answer at each temperature. Then it looks for agreement across all of them. If all those different creativity levels come up with the same answer, that's a huge sign that the problem is probably easy, and that triggers an early exit. The system just stops working on it, saving all that computing power for the really hard problems that actually need it. And this early exit idea makes a massive difference. By not wasting time on the easy stuff, this method cuts the total computational cost by nearly half, all while keeping those awesome performance gains. You get higher accuracy and a lower cost. It's really the best of both worlds. So, after all that, what's the big picture here? What does this mean for where AI is headed? Let's wrap this up. The most important thing to take away from this is a real shift in thinking. For so long, the name of the game has been brute force. More data, bigger models, more samples. This research shows us that smart exploration can be just as powerful, maybe even more so. It's not just about slamming your foot on the gas, it's about learning how to steer. And that leaves us with this one final fascinating question. Temperature was just a simple knob, a parameter that was there the whole time, just waiting for someone to play with it in this new way. So it just makes you wonder, what other simple settings, what other hidden dimensions are we completely overlooking right now? What other secret superpowers are just waiting to be discovered in the AI models we think we already know?